Hey guys, it's Miss Johnson here, and I'm here to bring you our last video for Algebra 2A. This is the back side of the 12, 4, and 5 notes. We left off with number 3, so I'm going to pick up here with number 4. Number 4 is still talking about independent or mutually exclusive events, events that don't have anything to do with each other, that don't have any overlap. We just have to decide, do we want to add them or do we want to multiply them? But now what we're looking at is a set of things where we're picking more than one thing. So here's what number 4 says. There are 7 girls and 6 boys on the junior class homecoming committee. A subcommittee of 4 people is being chosen at random to decide the theme for the class float. What is the probability that the subcommittee will have at least 2 girls? So we're picking more than one thing. We want 2 girls, at least. Okay, now there's 3 different scenarios that would give us at least 2 girls if you're picking 4 people. You could have 2 girls and 2 boys. You could have 3 girls and 1 boy, or you could have all girls, 4 girls. Okay. Now, we know that there's no overlap because there's not a person who can be a boy and a girl at the same time. That's just not possible. We also know that we are going to add these probabilities, and the reason we're going to add them, the reason they're mutually exclusive, is because we're happy with either one of these committees. We don't want all of these committees. We just want either one of them. We'd be happy if we had 2 girls, 2 boys, or 3 girls, 1 boy, or 4 girls. So we know we're going to add our probabilities. So we have 3 different probabilities here. We just have to add them together. Now, calculating these probabilities is where it gets a little interesting. We have to use combinations because we're picking more than one thing. So for 2 boys and 2 girls, the combinations of picking 2 girls would look like C of, there's 7 girls, so 7, choose 2. But I also have to factor in the combinations of picking 2 boys. So I'd have C of 6, choose 2, because there's 6 boys. And then I have to factor in the total. There's a total of 13 people, so C 13, choose 4, because I'm choosing 4 of them. So that's the total number of ways that we can just make a committee of 4 people. These, on the top, these are the number of ways that we can have a committee of 2 boys and 2 girls. So that's our first probability. Then we need to do the same thing for 3 girls and 1 boy. So the combination of 3 girls would be 7, choose 3. The combination of 1 boy would be 6, choose 1. C, 6, choose 1. And then the denominator is the same. The denominator is going to be the same for all of them because it's just the total number of ways that we can pick 4 people from 13. Then 4 girls, we don't need to worry about boys in this one. We're just picking 4 girls. We're not going to have any boys. So we just need the combination of 7 choosing 4. And again, the denominator is the same. So this is why we want to use our calculator to evaluate all of these values here. It'll save us a whole lot of time since there's so many combinations within a question like this. So I'm going to go through and find all of these in my calculator. The first one, C of 7 choose 2 is 21. C of 6 choose 2 is 15. And you can type some of these into your calculator as well just to check and make sure you're doing it right and you know where to find stuff. The bottom, C of 13 choose 4, is 715. Then the second one, C of 7 choose 3 is 35, and C of 6 choose 1 is just 6. There's only 6 ways you can pick 1 boy from 6 boys. So that one's just going to be 6, 715 on the bottom again. And then 7 choose 4, that's the only one on the top there. That's going to be 35 again as well. And 715 on the bottom. So then I need to go ahead and multiply all of these on the top. 21 times 15 gives me 315. So I have 315 over 715. And then 35 times 6 gives me 210 over 715. And then 35 is by itself at the end, nothing to multiply there. So then I need to add all of these up, add the numerators together. And when I add the numerators together, I get 560 out of 715. And I want to turn that into a decimal, which gives me 0.78. So there is my probability for picking at least 2 girls. I have 78% chance, basically, is what that's saying. So now we've taken a look at independent and mutually exclusive events, events that don't have anything to do with each other, but we also need to take a minute and talk about events that could possibly overlap. And there's two situations here as well. We have inclusive events, which would mean that we have some overlap that we have to account for, but this is also an OR probability, which means we're going to add. Okay, so inclusive events mean that we're going to add our probabilities together. The only thing that we have to take care of is we have to subtract the overlap. So let's take a look at example 5 and see what that looks like. Suppose that 1,400 students, of 1,400 students, 550 take Spanish, 700 take biology, and 400 take both Spanish and biology. What is the probability that a student selected at random takes Spanish or biology? So we're looking for an OR probability, which means we're going to add them together. So what I need to take care of or look at is the students who take Spanish, the students who take bio, and possibly the students who take both. I always want to ask myself, are there students who take both? So for the Spanish students, I have 550 students taking Spanish out of 1,400 total. So that's a pretty easy probability to write out. For the biology, I have 700 students taking biology of the 1,400 total. But now there's 400 students who are taking both, which means 400 students were counted in both this Spanish category as well as the biology category. And that doesn't really make sense. We can't count a person twice. They're only around once. We can't count them in two different places. So what I have to do is I need to subtract, that's where this comes in that formula, the both. Subtract 400 out of 1,400. My denominator is the same for all of them, so that makes life really easy. I would have 550 plus 700 minus 400, which gives me 850. And when I take 850 and divide by 1,400, I get 0.61 for my probability. Okay, so inclusive events, meaning there's some overlap here. There's some overlap that we have to account for. That's what it means for them to be inclusive. There's things included in both. Now, dependent events, again, there's going to be some overlap or some things that are changed from one probability to the other, but dependent events are ones that we want them to happen at the same time, which means we need to multiply. These are and probabilities. Like independent events, when it says this and that, find the probability of doing this and that, we need to multiply our probabilities together. So in number 6, it says, 3 cards are drawn at random from a standard deck of cards without replacement. Find the probability of drawing a heart, another heart, and a spade in that order. So we're drawing out 3 cards. We need the probability of drawing a heart, then another heart, then a spade. But what we have to consider is the fact that these are not being put back. Okay, not put back. So if I write out these probabilities, the probability of drawing a heart from a full deck of cards, there's 13 hearts total out of 52 total cards. So that's the first heart that I could draw. But now, once I take one of those hearts away, my hearts are going to go down to 12, and I'm not putting that card back, so my cards are going to go down to 51. So the second heart is 12 out of 51. And then I move on to spades. Well, my cards still went down because now I've taken out 2 cards, so now there's only 50 left, but neither one of the cards I took out were hearts, so I have 13 spades still. So let's just recap that again. The first heart, there were 13 out of the 52 total deck. And I took 1 heart away and 1 card away, meaning there's only 51 cards left and only 12 of them are hearts. Then I took another card away, so there's only 50 cards left, but I'm looking for a spade and all 13 spades are still there, so there's 13. Now I want all of these things to occur because it says and, so that tells me I need to multiply. So when I multiply fractions, I just multiply straight across the top, straight across the bottom. When I do that, I get 2,028 divided by 132,600, which gives me a probability of 0.15. Okay. Let's move on to number 7. Number 7 is going to be back to those inclusive events. It says there are 2,400 subscribers to an internet service provider. Of these, 1,200 own brand A computers, 500 own brand B computers, and 100 own both A and B. What is the probability that a subscriber selected at random owns either brand A or brand B? The fact that it says either and or tells me that I'm adding my probabilities because of that word right there. So what I need to account for is how many have A, how many have B, and how many have both. Okay, and the both are the ones that we have to take away. So for brand A I have 1,200 divided by 2,400. Brand B, there's 500 divided by 2,400. And the both, there's 100 divided by 2,400. So I need to put the brand A and B together, but now I need to subtract away the both because those people were counted twice. So I got to take them away. I'm going to let you go ahead and finish off this probability question on your own, and I will drop us down to example 8 and get you started there. So in example number 8, our last question, find the probability of drawing 3 cards of the same suit without replacement. So now it doesn't say which suit we care about. So we talked about what we have to do with that in our section with permutations and combinations. Now, I need to think of card number 1, card number 2, and card number 3. So for card number 1, that's just picking any old card from the deck of cards. I want them to be from some specific suit. I didn't name that suit, but there's 13 cards in every suit, so that has to be how many cards there are. So 13 cards out of the 52 total. Okay. Then the second card from the same suit. If I don't put that card back, now there's only 51 left. If I don't put that card back from that suit, now there's only 12 left in that suit. I take a second card from that suit, that drops me down to 11 from that suit that are left over, and 50 total. So here's the probability of the 3 cards. Now, here's where the tricky part comes into play. Because they did not specify which suit, it doesn't say if we want a specific suit or not. They just said find 3 cards of the same suit. There's 4 different ways that this can happen because this can happen for diamonds, for hearts, for clubs, or for spades. So I need to take these 3 probabilities and I need to multiply by 4. So when I type this into my calculator, I can treat this 4 as a 4 over 1 and put it with my numerators. I'm going to have 13 times 12 times 11 times 4. And then I'm going to have on the bottom 52 times 51 times 50. So what that gives me is 13 times 12 times 11 times 4. I get 6,864 divided by 52 times 51 times 50. Multiplying by 1 doesn't change anything, so I don't need to worry about that. 132,600. So I have 6,864 divided by 132,600. As a decimal, this is 0.052. So that is my probability. Okay. So independent and dependent events. Mutually exclusive and inclusive events. You have to decide a couple things. 1, do you multiply or add the probabilities? And 2, is there anything that overlaps or changes from one probability to the next? Okay. So that concludes our notes video series for Algebra 2A. Thanks for listening and good luck on your worksheet.